Hello YouTube, welcome back to Trustspector Gaming, and in today's episode we're gonna take a look at the math behind placing a satellite network around the planet of Kerbin. In my last episode I just started off just that thing, and one of the things that I wanted to know was, okay, how high should I actually put my satellites here? Because as you can see in this example picture, you want to have a free line of sight between all the satellites as shown here. If you place your satellite too low in an orbit, maybe 100 or 200 kilometers above the surface, well, you will have a big chunk of Kerbin in the way between your satellites, and you won't have as much connectivity as you would like to have. So I went out on the magical interwebs and searched around a bit. And the recommendations were all between, 650 kilometers, I saw 700, 750, that were about the range that were recommended, but I couldn't find any real reason to it or any post that described why you really needed to be at this height. So I thought to myself, maybe it isn't rocket science to really, pun intended, if you notice that, rocket science. It's not rocket science to figure this out yourselves, especially not because, since I actually studied a lot of math in school. So what do we need? What are the known facts here? Well, we have a triangle. And our satellites are evenly spaced around the planet. I'm not going to go into any detail of why this is the next thing that I'm going to talk about. It's what it is. But in a triangle like this one, with all sides that are in equal length, you will have 60 degrees in each corner here, summing up to a total of 180 degrees. In a triangle, the angles, the inside angles I should say, always sum up to 180 degrees. So that is something that is known, a angle of 60 degrees here. What else is known? Well, not much really. As I said, what we want to have is a free line of sight. So to accomplish that, we have something called the closest approach here, or I like to call it the closest approach to the planet Kerbin. And well, the closest approach for a signal between two relays here would probably be the surface of Kerbin. But I wanted to take some realism into the whole thing here and lift the closest approach up a bit, because I didn't want the signals to pass through the atmosphere. And as we know in Kerbal Space Program, the atmosphere is, well, it officially ends at 70 kilometers, and on top of that I wanted to add a bit of headroom for mistakes in placing out the satellite as well. So I ended up with any other known fact that I want the distance between the signal, the closest approach of the signal to the surface of Kerbin, and actually, yes, the surface of Kerbin, to be 85 kilometers. Okay, how does that help me? Well, with those known facts, not much right now. So what do we need to actually do any calculations here, to actually find a distance? What is the distance that we want to know? Well, the distance we want to know is the distance from surface or sea level of Kerbin up to our known, or the orbit that we would like to have. So how should we get that? Well, this point over here, the closest approach, and this point over here, they have to kind of come together somehow so that we can do some calculations here. We're going to use something called trigonometry. If you haven't heard of it, go look it up. But yeah, we're going to use, well, parts of trigonometry. We're going to calculate the distance here using something that is called a right angled triangle or a right triangle. So where in all this can we fit such a thing? If you don't know what a right angled triangle is, I'm gonna paint one for you here. So let's see here. We should have a base, flat base like this. We also have a side that goes up here, and to have a right angle triangle, the important thing is that here you have a 90-degree angle. Then you have the last side here to complete the triangle, and there you have it, a right angle triangle. This is the right angle here, and the angle of this, what you call it, the point or the side here and the one down here, they could vary depending on the length of the bottom and the standing line here, also known as something completely else, which I'm going to show you here. I'm going to take up a picture that I have. I would like to say I've borrowed the picture. Hopefully it won't be classified as stealing. I will provide a link down in the description to the site where I found it, so you can go there. You can find the picture in itself, and you can also read up upon trigonometry a bit better. But here we have the picture, and as you can see, we have a right angled triangle here, and if you have the angle down here, this is called the adjacent side. Opposite to that, you can see here we have the opposite side, and here we have something called, see if I can pronounce this correctly, the hypotenuse. I think that is pronounced correctly, or is it hypotenuse? Not sure. I'm gonna go with hypotenuse, although it sounds a bit like hippopotamus or something. Yeah. We have the hippopotamus, the lion, and the giraffe, and they were out on the savannah. No. It's the hypotenuse, yes. So here is the math that we're going to use. I'm going to go back to this picture here, and I'm going to bring forth I'm just going to leave you 5 seconds here and see if you can yourself find out where I will plot this triangle, this right angle triangle, and then I'm going to bring it forth for you. So take 5 seconds and just see if you can find it. Okay, hope you have figured it out yourself. If not, I'm gonna show it to you here. Here is our right angled triangle. The right angle being the 90 degrees here between Kerbin and the signal that we want to have. The known distances, as I said, is the 85 kilometer that I wanted to have above the surface of Kerbin for our signal, and well, currently that is the only known distance, but thanks to the wiki page, I'm gonna bring a link down in the description as well for that, we learn that for Kerbin we have a radius, an equatorial radius that is, and since my satellites will be deployed in the equatorial plane, we have an equatorial radius, that was a hard word to say, of 600 kilometers. And I'm going to show you that one. The radius, then equatorial radius, is from the center of Kerbin out towards the surface, just like, well, that, almost. So with 600 kilometers plus my 85 kilometers, we end up with a side here that is 685 kilometers. I'm going to bring up the previous picture here. As you can see here, we have, I'm actually going to take that one up. We have an angle, we have an opposite side and an adjacent side. And on our red triangle in the background here, the opposite side is the one that is this one. That is the one that is 685 kilometers. Now we have something we could calculate on. What we want to know now is, well, we want to figure out the distance between the surface and where should I put my satellite or my satellites. Well, we have 600 kilometers of Kerbin plus an unknown distance here. So let's get started to the calculations. We're going to go back to this picture and take a look. Opposite side 685 kilometers. What we want to know is this hypotenuse. How long is that? Well, we don't know for the moment, but the angle up here, as I said, in each and every corner here we have 60 degrees of angle. And this here that goes down to the center of the planet Kerbin, if we continue down here with an imaginary line, we end up halfway through the triangle. So this angle here, that is the half of 60. And yeah, with a basic math, we can find out that that is 30. So 30 degree angle and a distance of 685 kilometers. We can use one of these to figure out the length of the hypotenuse. Hypotenuse, yes. We have the opposite, we have an angle, and we have the hypotenuse. So the sinus of an angle equals the opposite length divided by the hypotenuse length. Well, that doesn't really give us anything, but if you have completed the first years of school, I hope, then you know that you can switch this one here with the one over there, and you will get the opposite side divided by the sinus angle will equal the hypotenuse. Hypotenuse, yes. So I'm going to bring forth a calculator here. Here we have the calculator. We have a known distance for the opposite side of 685 kilometers. We're going to divide that by the angle of 30 degrees, that is sinus 30 degrees, to get the length of the hypotenuse. So in the calculator program, you have to first push in or add 30 here and then press the sinus symbol. Up here you can see we now get the sinus 30 as the equation said. Then we could press this one and we will get a hypotenuse distance of 1,370 kilometers. So there we have it, you would think. No, we don't. This is the distance, the total distance here. So what do we have to do? Well, we have to subtract the distance of Kerbin here from the center of the planet to the surface. And what was that? You guessed right, 600 kilometers. So subtract 600 from that, and guess what? 770 kilometers. So that is how I calculated that I would like to place my satellites at a orbital height of 770 kilometers above the planet Kerbin. As I said before, people are suggesting everything between 650 to 750 kilometers, and although that those height works as well, the closest approach to Kerbin here will be inside the atmosphere. I think for a 700 kilometer orbit, the closest approach will be at 50 kilometers above Kerbin's surface. So that's 20 kilometers inside the atmosphere. And even though the Kerbal Space Program, game mechanics and such doesn't do anything with radio communication signals, I still wanted to make this a bit more realistic and put my closest approach outside the atmosphere. So yeah, that was I think everything for me for this video. If you want more kind of this content, don't forget to like and subscribe. And until next time, have a great day. Starspector Gaming signing out.